In this video, we're going to talk about errors and exceptions. So the primary mechanism to deal with errors and exceptions in C++ is the try block. And this is what it looks like. You have a try block that starts with the keyword try, and then you have a compound statement, which is followed by a bunch of catch clauses. Now, the book calls them catch blocks. This in the standard is more often called catch clauses, but they really mean the same thing. So you have code that's running in this try block here. And then if it throws an exception, it may be handled by one of these catch clauses, which are also called exception handlers. And the way this works, let's take a little closer look at how this works. So suppose you actually throw in an exception object. This is an object here. And what actually happens there is that it's going to create a temporary object that typically is a copy of the object you're trying to throw. And then before it goes into one of those exception handlers, it's going to actually exit out of this block, just like a function returns. What it will do is it will call the destructors on the automatic objects over here in this try block here. And then if it finds a exception handler that is able to handle this parameter, because the parameter type matches the exception object. Now, this could be the same type, or this is a base class type of a derived object. And you may have other handlers that can handle that same thing, but it's going to find sequentially the very first one, and that will be the one to be used to handle that exception object. That exception object is passed into this catch clause, just like a function call. This is a catch clause, is just, you can think of it as almost like a function, but except this is tied to this try block. It can only be used to handle an exception thrown out of this try block. And then so that parameter, the argument is passed into this parameter, and this parameter EX here, if you're trying to reference this variable inside this catch clause here. So that's basically how that works. And then once it's caught, let's say you don't rethrow that exception out again, and then the execution will continue from the very last, the statement following the last handler of the try block, and we'll continue forward. So that's kind of the mechanism of throwing in a catching exception. Now, the exception does not have to throw directly from that try block. It could be because of a function call. Let's say you call this function fun1, and the fun1 is like this. Inside fun1, it calls, fun3, and then let's say fun3 actually somewhere throws an exception. And that exception, once it's thrown, what the runtime will do, the C++ runtime is going to unwind. Now remember, when this do function calls, it's going to have maintain the state of the function invocation in a stack. So what it will do is it will unwind the stack. So it's also called stack unwinding, going backwards to look for an exception handler. It's going to look for, first of all, inside the fun3, is there a try block here, right? If it cannot find one, it's going to go upward to the function that called function fun3 and up the call stack. And then you see fun1, whether it's going to look for if there's any exception handler that can handle that exception object that's thrown out of fun3. If it cannot, in this case, let's say it doesn't have it, and then it comes down all the way to this level where fun1 is called, and then it does find a exception handler that is capable of handling that object, the exception object thrown out of fun3 multiple levels deep. And then you will, this object will be passed on to this exception handler, and then you have the relevant code to handle that situation. So an exception doesn't have to throw directly. You have a throw statement here from this try block, but it could be many levels deep somewhere. An exception bubbled up to over here, then you catch it, right? So what if the exception is not caught, right? So here we found an exception handler, but what if there's no exception handler? Well, it's going to go all the way out of until your main function, the entry point, right? And then so you don't have anything that catches that exception. Then what the runtime is going to do is going to call the terminate function. That terminate function essentially will call the abort. So your program will terminate and basically it crashes. And the library does allow you to designate your own terminate handler, but this is rarely used. You probably normally don't have to worry about this. And the scope of a try block. So the idea with this the exception handlers is the catch clauses, they are tied to a particular try block. They don't mix together. This exception handler cannot handle, let's say, an exception thrown over here down below, or this catch clause cannot catch an exception that's thrown out of this try block, right? They are not they're unrelated, right? So they cannot be mixed together. So you see, this is kind of the scope. If you define a variable inside this try block, and just keep in mind, this is almost like a function scope, right? This is actually, it defines a scope here. And so if you have a variable defined inside here, that variable is not accessible inside your catch clause. Okay, just remember that, because this starts a new scope. Then over here, you can access your parameter here, the exception parameter right here. That is fine. And also the variables defined above, outside this try block, that will be accessible as well. So if you need to access some variable, that you're operating on inside the try block, inside later on when you do exception handling, you still want to access that variable, then you need to declare that variable outside, above the try, outside the try block, and then you can access that inside your catch clause. And then of course, you can actually nest these try blocks. And then so this becomes, so here, if you throw an exception into the inner try block, if you throw an exception, and let's say this exception object cannot be handled by this exception handler because the type mismatch, and then it will go up remember this, it will go try to find an exception handler in another try block that's actually enclosed in the outer try block. Is going to look for, is there an exception handler here that is capable of handling that object that will throw out of there inside. So that's kind of how the runtime is going to look for an exception handler for a particular exception that's thrown inside a nested try block. Of course, it can be many levels deep if you want, but practically speaking, normally you're not going to see more than 2 levels deep. Otherwise the program is not a good style. You probably want to break that into functions instead of having everything together. It's just hard to read. And you can rethrow an exception. So sometimes, let's say you throw an exception right here, and then you catch it here. But then you try to examine this exception, maybe because let's say you have a inheritance hierarchy there, and then maybe out of the derived classes, you're only interested in, let's say 3 out of the 4, but there's one type you don't want to handle. You want to leave that to an exception handler outside, to some other exception handler. That often happens, by the way. And so what you do is just in that case, maybe you have some kind of a sort of a if condition to check, okay, this is something that you don't want to handle, then you just rethrow that out of the uh, catch clause. And then so the runtime is going to go look for another exception handler that may be capable of handling it. Okay, so you just use this throw keyword without an expression after that, and this will rethrow the original exception object. Okay. What if you want to catch all the exceptions? You can catch all exceptions with this ellipsis parameter. So with a dot, dot, dot. Now, the issue with this is you don't have a way to access that particular object. So it's not really that useful. Maybe during debugging, sometimes, I mean, even during debugging, you're not seeing this object, so it's not going to be very helpful. So yeah, technically you can do this, but it's not really commonly used. Now, you've seen this try and catch. Where is the finally, you wonder, right? So you've seen finally clause in many different languages, such as Java, Python, JavaScript, right? C#, and Swift, you name it. Well, in C++, you don't need a finally clause. The reason for that is because of this write idiom. We mentioned this write idiom before. When we talk about smart pointers, why we use smart pointers. And the write idiom, and the write just, it's short for resource acquisition, is initialization. It's a mouthful. What does this mean? It means to bind the life cycle of a resource that must be acquired before use to the lifetime of an object. So you have a sort of a write object that is initialized with a resource, and that resource has to be acquired for that object to be initialized. So once the object is initialized, the resource is always available until the object gets destroyed. And in the destructor of the object, the resource is released. So that's what it means to bind the life cycle of the resource to the lifetime of the object. Now, why is that useful? Let's take a look at an example here. Now, we really haven't discussed, this is really another focus of this course, about multi-threading or concurrency programming. But there's this concept, maybe you're at least familiar with this a little somewhat. So there's a thing called a mutex. Mutex is, it's called a mutual exclusion. It's a object that's used to essentially protect a critical block of a code so that only one single thread can access that block of code at the same time. So, I mean, because when you have multiple threads accessing that same block of code, perhaps there will be a corruption of some kind. And so you want to protect that block of code. Is like, it's also called the critical region. So this is, let's say you want to achieve that with this function called bad. Okay, so the typical usage pattern is that the mutex supports is like a lock. It's a two operation. You can lock it and then you unlock it. So once you lock it, whoever the thread that's uh, obtained the lock starting from here, then this is the only thread that can access um, this code that's following at that time. So there will not be another thread, using this block of code at that time that may cause corruption in the state of the variables. And once it's done, and it will call this unlock, it'll release the lock and then things will be done and back to multiple threads running at the same time. So the problem with this here, though, is if this f function throws an exception, then the mutex is not unlocked because the execution stops here and it gets out of this bad function, right? And then that's one case. Then if this doesn't throw, and here you say everything is okay, if that is true, then you proceed, that is fine. But if there's a problem, if there's some, if this is false, and then you'll do an early return, right? So something happened there, although it's not throwing an exception, it just returns a false value. And then in this early return case, the mutex is not unlocked either. This statement that's supposed to unlock it is not executed. Now, of course, if you look at this, let's say, well, maybe I can solve some of this problem with this try catch we just learned, right? The try block. With the try block, yeah, you may solve it with a try block. Yes, but then you also have a statement there, this unlock statement. This here, you want to be able to release the mutex regardless whether you succeed or not. And this is the situation where typically in the other languages, you want to put this thing in a finally clause. So it will be executed regardless of what's happening in the try block. So but then in C++, we don't really have that. So the mechanism to deal with it correctly is that you use this RY idiom. So this lock guard is a simple wrapper that wraps around this mutex object. And this enforces this RY paradigm that it will be able to basically when you create this LG object of a lock guard, and you're initializing it with a mutex m, and so the mutex will be locked when it's trying to create this lock guard object, and then so basically is acquired resource. The resource is acquired at the initialization. That's why it's called resource acquisition as initialization. That's really what that means here. And now then you call this f function. F function may throw an exception. If it does throw, it exits out of this function. This function returns, right? Or in that case, though, the destructor, because of how that exception handling works, the destructor of this LG object will be called. And then when that is called, this inside the destructor of this lock guard, the lock will be, the mutex will be unlocked. So essentially the resource will be released. That's really what the RY is about. So that's why it's safe. The mutex will be released. And then if you also, in this case of early return, and same thing, the M will be released as well, because this unlock operation is going to be in the destructor, and they will be always called when the LG object is out of scope. Okay, so it's an automatic variable here, and that's what we call this lifetime of this object. When the life of this object ends, the resource associated with that is also released. So that's the idea of a RY idiom. Now, there are also cases where you say, I want to, I don't want to throw an exception. So there's this no except specifier you can use. You can signify that your function does not throw an exception. Now, this has many purposes. One, of course, is like a documentation. You're telling people if this is a part of your public interface of a class, and people will see this, okay, this is not going to throw an exception, so they don't have to worry about, handling a potential exception thrown out of that function, right? But also, in the case that there's if it actually does throw an exception, and then the runtime will actually just terminate. It will call the terminate function, right? The standard terminate. That is unexpected error. Essentially, that's what that would be called a bug in a program. Okay, so that is actually a desired behavior. The right behavior here is to terminate. And so this no except is a guarantee. It will not throw an exception, otherwise program will crash. Okay. And then a related thing about no except though is there's an operator called no except. Here's an example. Now here I use this struct. As I mentioned, the struct and class, they are almost functionally equivalent, except by default, the members, if you don't declare the access specifier, right? And then by default, they're public. I just want to save space here. I just basically, for this slide. So that's why I use struct, okay? But otherwise, it's the same thing as a class. And so I define a default destructor here. This is explicitly defined. In that case, I have a comment here says destructor prevents a move constructor. I'll explain a bit more when we get to talk about the move semantics. But for right now, the idea here is so that we're trying to verify the copy behavior. So we want to basically disable the move behavior. And then if you don't understand what move means, and then we're going to talk about that just later this week, okay? And so we have a class A, which is pretty much empty, and then we have class B, we have a member variable here called m_v, which is a vector of integers. Now, this vector just, if you look up the definition of a vector in a reference book, the copy constructor of a vector may throw. Okay, so it may throw, what does it mean may throw? If you have a function that does not have the no expect specifier, that it means it may throw. There's an exception to that. For example, the destructor. The destructor, even if you don't have the no throw specifier, it's implicitly no throw, no except will be added essentially by the compiler. So that's why you don't see no except in the destructors here. Now, now we're talking about the copy constructor. The copy constructor of this vector, actually, it may throw. And then because of this member variable may throw, then as you see, as we know, the copy constructor for B class is going to be also generated, right? There's a default copy constructor. And because the member variable may throw, and that copy constructor of B also may throw. It may throw an exception. So it doesn't have the no except specifier in the defaulted copy constructor. And then the typical usage of this no except operator is like this. Now here, it can be a little confusing though. So let me explain this a little bit. Now this is the function template. It doesn't really do much. It just, returns a copy of the object that you pass in, right? And essentially by doing this, it's gonna it's going to essentially just make a copy using a copy constructor. So that's what we're trying to test the behavior here. And then you may want to declare this function template with a no except specifier. Now the no except specifier takes an argument actually, optionally. If you don't have an argument, that's fine. That means that will not throw an exception. But if it does take an argument, that will be a Boolean value. It could be true or false. In the case of the specifier that does not have a argument, then that just means is equivalent to no except with the argument of true, right? It means no except. But then what this allows us to do is, this is a specifier, by the way. Inside that specifier, this argument for the specifier, actually you can use a no except operator. And this is an expression that's using the no except operator. This is trying to test. Now you see this T type, okay? This is the template parameter T, right? T with a argument of O object. You see, this is essentially using the copy constructor of making another object out of another one, right? Is using this is essentially just this expression, right? Is using a copy constructor. This you can recognize. And what this will do is this is going to be compile time, okay, not runtime. At the compile time, the compilers are going to determine the value of this operator, the no except operator, to see if this copy constructor actually throws or not. So in the case of A, the defaulted copy constructor by default is no except. Basically, it throws no exception. So if you're going to pass in A here for this function template, and then this is going to be no except with this value becomes true. This operator, you're basically examining the no except specifier of this copy constructor, right? And then in the case of a B, because the copy constructor does not have no expect specifier, in that case, it would be false. So that's really what this is testing here. We are using this no except operator to evaluate an expression. This expression here is actually, we're calling a function. It's from a function template, right? So we are using a object A here, and then the next statement is using an object B and making a copy and trying to test if this is trying to test if this copy function it has no except specifier or not. So this is verifying whether this is taking an argument of a true or false, right? If it's a false, that just means it's the same as if there's no except specifier. Okay, so it's a little confusing because no except is a negative term. Just, I hope you get it. So you can run this program if you want to see this. Basically, the result of this is matching the usage of a no except operator right here. This is a and the same thing. This operator is evaluated at compile time. If you have 90 that supports it, you hover over this expression, you're going to see a true or false value directly, right? Okay. Now we'll talk about exception objects and how do you make exception objects? Do you make your own exception classes? Yes, you can. Now, before we go to our own exception classes, let's take a look at the standard. The standard actually has defined many exception classes and in a hierarchy. And this class hierarchy all has a common base exception. What this allows you to do though, right? Essentially, you can catch all exception with a catch clause that takes a parameter of exception type, right? So that's convenient. So I'm not going to go into talking about each one of them. You can still need to look up the reference and see what they are. Typically, the idea is if you can reuse the standard exception for your situation that kind of makes sense, the semantic matches, then you should use it. Otherwise, you can make your own. When you do make your own, it's a good idea to derive from one of the standard exceptions, maybe from the base one, the exception, or even for some other ones that it seems like a good match. So you want to probably read up a little bit about them if you want to use and pick a appropriate one. If you don't want to pick a appropriate one, just then at least derive from this exception class. And then what does the exception class look like? The exception class look like, this is the public interface here. And it's simple, it's got a default constructor. It has a copy constructor and then, copy assignment operator. Then it has a virtual destructor and also another virtual function that is called a what. Gives you a message if like what was wrong. And yeah, so this obviously gives you the polymorphic behavior when you have a exception handler. It takes an exception parameter, and then that will basically, if you call this a what, and that will give you a message that kind of tells you what's wrong. Okay, so that's actually, let's take a look at some code before we get to summarize. So there is let's take a look at an example of this. Okay, so here, now we have to be careful about, this kind of explains why the RAI is a good idea. So the RAI idiom. And so here we have, let's say, you call this function compute values, which returns a pointer to double. Okay. And then we know this is a raw pointer. We're going to, well, this actually returns an array, actually, a dynamically allocated array. So computer values, as you see, allocates a on the free store using the new operator to allocate an array, and then returns a pointer to that array. And then of course we want to deallocate, but the problem with this is if that throws an exception, it won't reach this statement. This delete never even happened if there's an exception here. And then you get to this exception handler here. So what you're going to do, and then you have a memory leak. Okay, that's really what this example demonstrates. You have a memory leak. Well, you may say, well, I can solve this problem this way. Yeah, you can solve the problem like this. For example, you can solve it. You can just say declare it outside, this, as I mentioned earlier, and then basically, and then you use it like this, right? And then perhaps, you're gonna do it right here. Then you say, I'm gonna deallocate. Well, what if this is throwing exception is not the trouble type? Well, you say, well, maybe I'm gonna just catch everything, right? But this kind of gives you the finally, the finally that we were talking about. Okay, where is the finally? Perhaps you do that, but that's ugly, right? That's not what we want to do. This is actually not a good idea. So let's look at a RAI. The RAI solution, let's take a look at this. Now, is this the RAI solution? 17B. well, this right is kind of halfway. This actually did not finish the whole thing though. So what this is saying is that computer values here, instead of using the new operator, we're going to make this is uh, a RAI EDM powered array, right? So because essentially you're creating a array. Think of this as like we have a standard array and power. Yeah, of course, you want to use that instead of your own thing. But again, this is kind of the idea. This double array RAI, and then because this is a automatic variable, right? If you here, but we're still returning a pointer though, and that means, and we're calling this release. It will return. It will release that pointer, the raw pointer, out of it. So actually it will not get deallocated. Of course, you do want to keep that around. So that underlying array is still there. And then you're still responsible for deallocating that array. Now, this is still the same problem. It's not really solving the problem, right? So instead, really what you should be doing is you say, well, I'm going to return that right object, right? You don't want to just turn it back into the raw pointer again. Okay. So let's say you want to just return the right object. And of course, then we're going to pass this on. Then you don't need to do the delete. Of course, when this values goes out of scope, if this throws an exception, which it does, right? Based on the logic here, let's see what's wrong here. It's a deleted function. Values. Opening a right object. Oh, the reason this is giving an error because look at there's no copy constructor, so we cannot return that. Yeah, we deliberately deleted this class has the the copy constructor deleted. That kind of makes sense because, well, so here we're not doing a copy. So it doesn't really work well. This right as is designed, it doesn't really work. So the book already suggests actually the way you really solve it. This is kind of demonstrating the issues. The way to solve it, obviously, you want to use the unique pointer, right? And then you can pass the unique pointer around. Now, of course, again, you can probably just enable the copy, but again, so if you want to do that, but this is demonstrating some of the issues with rolling out your own Ryan classes. But so if you want to, you can use the standard one, use the standard one. Okay, so another example I want to show is just kind of go through that a little bit. So that box, back to that box problem, right? The whole running example throughout the book. This shows you, let's say the box dot volume throws an exception, and then you can cast the exception with the standard exception because the exception thrown out of the volume. Well, actually, it may not be the volume, or maybe the constructor that throws actually. I think it's one of the constructors does throw an exception. So if you look at that, okay, that's for exception. This is very typical in a constructor, by the way. You want to validate the parameters that's passed in, make sure they're valid. And then if they're not valid, it throws some kind of exception. Okay, so in that case, this exception is actually derived from a out of range. It's a standard exception, which is obviously uh, which actually is derived from logic error, and logic error is derived from exception. Okay, so remember that hierarchy that we showed. Okay, so this is just kind of showing you a typical usage of your own uh, custom exception type. Now, what is involved to make this one? So you have a constructor that, in this case, we want to take a specific value that's we're interested in for this particular exception type. And then we may also want to get the value once you catch this object in an exception handler. This will give you access to that value. So this is a very typical way of doing it. And then you may want to initialize the base class with a message. Typically, the main thing is the message or what the error message that you want to display. So that's really kind of what is involved. Typically, that's what it takes to create your own exception class. Okay. All right. So let's summarize. Exceptions are objects that are used to signal errors in a program. Technically, you can use any type, including the built-in type or maybe even an integer, but that's not good programming. So typically, you do want to use class objects. And the code that may throw exceptions is usually contained within a try block. So you want to, if you do care about that particular exception, you want to handle it, you wrap that in a try block. And the exception handlers are placed in the catch clauses of a try block. So, and those exception handlers are tagged to that try block. They don't catch exception in other try blocks unless they're in their try blocks that are nested. Of course, they can still, as the control gets out of the inner block, then the exception can thrown out and it gets handled by the outer try block. That is a possibility too. And the try blocks can be nested, as I just said, and the catch clause with a parameter of a base class type. So this is really, so the catch clause takes a parameter, and that parameter is if it's a class type that, it can take an object that's a derived class type. And then a catch clause with a ellipsis parameter catches all exceptions. And that is not used very often. So you do have access to that, but it's not very used often. And as I just showed, actually, it's you may use that as a finally kind of thing, but it's just not necessarily a good programming habit. And then so that there's the standard terminate function that can be invoked if there's an exception that's uncaught. So it has not found a eligible exception handler, then the terminate will be called. So the write EDM, you do want to use that, program. This is what makes your program, safe, and then it's easy to use. So every resource should be acquired. A resource like memory, you want to allocate something, or it may be a file handle. It may be as a socket for networking. Anyways, so any kind of resource. Also demonstrated a mutex resource for concurrency control. So they need to be acquired and released by a write object. So this way, you don't really need to use new and delete operators anymore. In the place where you do use it, that would be like maybe you may deallocate something in a destructor. Even that is going to be rare because the standard patterns using arrays or collections, there's already standard classes you can use. You don't need to roll your own. The no exception specifier indicates a function does not throw exceptions If it does, program basically crashes because the invocation of terminate. And destructors should never throw exceptions. Technically they could, but they should not. Otherwise, just for good program design. And the standard exceptions, you want to use them as much as you can, or derive from the standard exceptions for if you are trying to make your own. Here's a golden rule for exceptions. You want to always throw by value. You don't throw a pointer or reference. You want to throw by value. And then when you do catch in the catch clause, the exception handlers, you want to use reference to const. And then when you rethrow an exception out of a catch clause, then you want to just use a throw statement without an expression. If you use an expression, let's say you the catch clause take a parameter, the parameter name is ex, then you inside there you want to rethrow that ex. Problem is it's going to make a copy of ex, and then most times is not a good thing because in the polymorphism, right? If we study that, that's going to cause, if it's a derived object, that will be sliced to only contain the base object. That will be the one that will be thrown out. And then you lose the specific exception type. That will be a problem. That's not what you want. So just use the empty throw. Just throw without an expression. If you do want to rethrow, just use that. Okay. That's all I wanted to share. Thank you.